Hi, this is Yuga Ojima from Aerospace Engineering at Georgia Tech. Level 4 in A2610 was conducted by the group A10X. I'm going to present about Rijke Tube. So, the purpose of this lab is to study periodic fluctuating properties and acoustic oscillations in a pulse combustor. The phenomena is caused by heat release, pressure, and velocity oscillations, which are coupled and feed on one another as shown in the top and middle figures. The strength of the oscillations grows until the acoustic driving is balanced by acoustic losses in the combustor. Such combustor has many advantages. For example, a pulse combustor is used for mixing fuel and air in order to increase the combustion intensity. In addition, a pulse combustor is employed to push the combustion products out of the exhaust as shown in the bottom figure. In this lab, a Rijke tube, as shown in the top figure, was used to investigate the phenomena. The tube consists of a vertical tube with a burner placed at the 1/4 of its length from the lower end. A Rijke tube acts like an organ pipe when the phenomena is observed. A scale is also attached to the tube to measure the burner's height. A black tube, as shown in the top figure, is a photomultiplier which is used to measure the heat release rate. A bronze-colored piezoelectric pressure transducer, as shown in the bottom figures, are used to measure the acoustic pressure fluctuations. The transducers convert the pressure to the stresses, strains, and finally voltages. A remote control, as shown in the left figure, is used to position the burner and control the propane fuel. A fan, as shown in the right figure, produces uplift flow and induces acoustic oscillations. We obtained several raw data. A thermostat was used to measure the room temperature, which was 78 Fahrenheit, as shown in the top left table. A ruler was used to measure the length of the tube, which is 70.5 inches. The distance of the upper and the lower transducers relative to the central transducers are 18 inches. The top right table shows the 4 experimental conditions. The 4 conditions include the closed valve and 0-inch height, the open valve and 0-inch height, the closed valve and 2-inch height, and finally the closed valve and 5-inch height, which the acoustic oscillations ceased. We also checked the height when the oscillation restarted, which was 0.8 inches. The bottom table shows the root mean square fluctuation of pressure field in voltages at 4 different conditions. The peak frequencies and phase angles are obtained by the computer generation. Ones in the top tables mean that there are no acoustic oscillations. As you can see, the phase angles between the transducers are 1 degree apart. Also, the results indicate that as the distance between the transducers and burners increases, the phase angles also increases. The peak frequency is approximately equal to the estimated value of its resonance frequency, 96.7 Hz, which is obtained by the equation where A is the speed of sound and L is the length of the tube. There are multiple steps to obtain this sound pressure level in terms of decibel. First, we use a pressure transducer calibration curve as shown in the right figure, which converts the voltages to pressures. The slope of the linear equation is approximately 96.3. From the curve, the PSI values are obtained as shown in the bottom table. Finally, the sound pressure levels in decibel are obtained by the equation. The sound pressure levels are above 130 decibels, so that those are considered to be in the range of the threshold of pain. Also, we obtained the relative phase of the pressure and the radiation signal by calculating the difference between each signal and the signal from the middle pressure transducer. In summary, the lab showed that in a Rijke tube, as the distance between the transducer and the burner increases, the phase angle also increases. Second, the length of the tube can be used to estimate its resonance frequency. And third, a Rijke tube could produce high sound pressure levels which could be in the range of the threshold of pain. That's all. Thank you for listening to my presentation.